Just laser pointer. There we go. Okay, ready to go. Good morning. My name's Tom Miller. I am a PhD student at the University of Sydney. I'm doing my research under the supervision of Pierre Rognon and Itai Einav. And this work has also been done in collaboration with Blo Metzger, who's here today from CNRS Marseille. I'll be talking to you today about stadium shear experiments I'm doing, and I'll explain what that actually means. And then some interesting results that we got, that we weren't expecting, which, as happens, sort of led us down a different path onto this eddy viscosity inspired model for dense granular flows. So originally, my project had its origins in heat generation within dense granular flows. So the idea that through the interparticle contacts, you have heat generation. And also, it was driven by the idea of this heat flow paradox, where in certain events, such as the San Andreas fault here, where we have large shear deformations, current measurements of the heat that's generated do not match what is predicted by current models. So this was the original motivation of my project. Along with that was some work that Pierre and Itai had done in 2010. And that was on this idea of granular convection and granulance. The idea that correlated motions or convective motions within a sheared granular media can greatly influence the transfer of heat within the system. And in fact, Pierre found that there can be a few orders of magnitude increase in the heat flux through granular convection, and that this is often ignored in models of heat. So I came in at the point where we were looking to do something experimentally to look at this, which is not an easy task. So some of the basic requirements we had going into this when we started thinking of what we could do is that we wanted large plane shear deformations. There's some really beautiful experiments that already exist, but they tend to be limited in how many shear deformations can be achieved. We can have cyclic shearing, go back and forth, or we can have 1, 2 shear deformations, but it's somewhat limited. We also wanted to be able to analyze the flow at the grain scale, so we wanted to see individual grains and how they behaved. And we wanted to be able to measure or control the shear rate and shear stress and normal stresses as well. We could. We wanted one order of magnitude at least in the shear rates. And this is what we came up with. The stadium shear device. It's actually relatively simple, but looking back, it always seems that way. We have here what is essentially an automotive belt that runs around 2 sprockets. One of them is driven here by a motor and gear assembly, and the other is just an idler sprocket around which it moves. The grains, what is a very important point here, which is maybe not so obvious, is that the grains can actually recirculate underneath the sprockets. So the sprocket is raised above the grains, so that's why you see this additional height of belt, so it can go around the sprocket and the grains can recirculate underneath. The grains are very simple for these experiments. We just have nylon grains. Cylinders about 10 millimeters high of 3 different sizes, and they sit on a glass plate. We also have this roller assembly here, which we use to control the volume or apply a normal stress. So if we zoom in on the roller assembly, what we see here is that we have some load cells to measure the loads applied laterally, and we have some constant force springs here, which are quite a revelation. They can quite accurately apply a fixed load. And if we want to do fixed volume experiments, we can simply clamp our linear sliders here and fix the volume. We also have on the motor assembly, just hidden in here, a torque transducer, which allows us to backfigure the shear stress acting on the material there. Okay. So this is the top view. and some of the parameters that we have 12, 15, and 20 millimeter grains. We have roughly 1/3 of each in the system. There's about 2,000. And that gives us an approximate 20 grain diameters across the flow. So it's a relatively narrow flow. This is what we're doing. We're rotating here, and the belt goes this way, and we can apply stresses or impose a volume that way. What we do is we film from above. We have our region of interest here in the center where we have plane shear developed, and we film from above, which allows us to track the position and movement of the grains. So I'm just going to show you very quickly now. If I can find the cursor, there we go. What we sort of get from these images. We have the red lines here as well. Obviously, that can give us the orientation of the grains. So we can get quite a lot from this position, orientation of the grains. And we can do this really for as long as we want. So the particle tracking is quite robust. We use a circular hoof transform to detect the center of the grains, center and size of the grains. And then we can cheat a little bit, because if we know the center of the grain, we can just look at a small window around the center of the grain and do a hoof transformation to get where the orientation of that line is. So it actually makes it easier to then get the orientation. And we can do this through time. So obviously we have a lot that we can do with this. Obviously I don't have a lot of time today to present it all. I'm going to restrict it to a series of tests that we did in which we had a fixed volume condition. Now, we've heard yesterday about the advantages of fixed pressure over fixed volume, and I can certainly agree, but we didn't have the facility when we first started with the fixed pressure, so we fixed our volume. If we look across the flow here at average diameter and solid fraction, it's fairly consistent. We have some drop-off of the solid fraction and the average diameter. Quite simple reason for that is that our smallest grain has a preference to getting stuck in the belt due to its size, matching the size of the asperities. We can also see in the solid fraction here that there is some layering at the boundary, which would be expected if grains are sticking in the boundary. So the tests I'm going to talk to you about today, they're performed for a constant solid fraction, approximately 0.78. We looked at 8 different shear rates. That's not a minus, that's just the bullet point. So from 0.08 to 0.8, so they're relatively slow. We're certainly in the quasi-static regime here. We pre-sheared the system for quite a long time. We wanted to ensure that the system had time to rearrange and reach a steady state. And then we also tracked for quite a long time, 100 shear deformations. And we were expecting to have linear velocity profiles, and this is what we got. We got this S shape. We weren't expecting that. We've seen S shapes in simulations, but they tend to be for much higher inertial numbers. We have quite low inertial numbers here on the order of 10 to the minus 4, and we were not expecting anything to be doing this. So we scratch our heads for a while. What we notice, which is quite nice, is when we normalize these velocity profiles by the belt velocity, we get this collapse on the curve. Now, while the S shape in these tests is not significantly pronounced, it's very clearly not linear. So we wanted to investigate this further. When we look at the shear rate profiles, it's even clearer that we don't have linearity because we do not have constant shear rate profiles. We get these sorts of profiles for our shear rate. And again, if we normalize by the nominal shear rate, which is the belt velocity on the size of the system, we get this collapse of our shear rates, which sort of follows from the collapse of the velocity profiles. So what could this be? One of our first thoughts was base friction. Okay, we don't have a frictionless base. We have a glass base. It's relatively low friction, but it still could be a factor. So if we introduce friction into our momentum balance here, and then using a Bagnall's scaling, what we would get is this effect of friction on our shear rate profile. And what we find is that qualitatively, for a particular setup, that this could provide an S shape, but it cannot account for the scaling of the shear rate with the belt velocity. We just couldn't get it to work. So we look at what's happening with the grains themselves, and we see something interesting. On the top here we have the velocity fields, and on the bottom we have the fluctuation velocity fields at 3 different points in the shearing process. What we quite clearly see is these correlated structures, these rotational structures that do exist. They tend to form and then break up. So they're not always there, but they are always forming and breaking up. So we have these correlated structures within our system. These have been seen before. And in fact, Rajai was sort of introduced this term of granulance. But we think that this could be behind what's causing our S shape. So we keep searching. And partly, these structures have led to reformulations of our local relogical models into what's called a non-local model. Olivier Poulecan, who's here today, one of the models is this self-activated process, and another is fluidity, the sort of the 2 main ones that we were looking at. And they both work well for what they're doing, but the role of the wall is somewhat unclear to us in these models. So there has to be an assumption about whether the fluctuations are reflected back into the flow or absorbed by the boundary, and they can lead to somewhat different flow predictions. So we looked sideways and we looked at what people were doing in fluids, and for quite some time now it's been known that a boundary can cause turbulent eddies, and we thought we would sort of draw on this concept and see if it could produce anything for our flow, because what we're seeing here is certainly boundary effects. So while the Bagnall scaling is not sufficient to explain this non-constant shear rate, he does introduce this idea that the kinematic viscosity scales with d squared and the shear rate. So there is a length scale and there is a dependence on the shear rate here. As we're seeing these large structures where the length scale is generally much greater than the particle diameter, we could expect that the momentum would transfer over such distances. So we're introducing a mesoscopic length scale instead of on top of the grain diameter. If we had no boundary walls, we might be able to assume that if this was sort of the extent of a correlated motion, that it could be much larger than the flow width if there were no walls. So we could have a big correlated motion. But once we put the walls in, our idea is that these correlated motions are truncated by the belt. So we have this sort of reduction in the available size of our correlated motions. And in fact, if we have one that's closer to the wall, we're saying that its size is truncated by distance to the wall. So that if we introduce a mesoscopic length scale, it's going to be proportional to the distance to the wall. That's what we're trying to do here. If we put that into the Bagnall scaling, so the idea is that we have an additional term here that is proportional to the distance to the wall. We can get a prediction, so A here is just some constant of proportionality. We can get the following prediction for the shear rate profile here. And just to simplify that, we've made gamma.h this. Okay. So we can derive the shear rate profile. And in this equation here, the only unknown parameter is A. And what's really nice about what we've done, and it is fairly simple what we've done, but But what is nice about it is that the only unknown parameter in this equation, A, can be shown to be this. And from our experiments, we know what D on H is, about 0.12. And we know the ratio of the shear rate at the belt and the center, which is approximately 2. So we can get this parameter A. So I will somewhat conclude on what this model prediction gives us for our shear rate profiles, and then just mention briefly what other work we've been doing. So the blue line here is the average of those shear rates I showed you before when we collapse them all onto the one curve, just to get rid of some of the mess. And the red is our model prediction. It's quite good in the bulk. We have a slight deviation here, which we are looking at refining on. But overall, for such a simple model in which we can determine all of the parameters, we don't have really any sort of variables that we just vary to make it fit here. We get quite nice agreement, and we're quite happy with that. So what else we're doing? We're looking at grain rotation, obviously. Now we have the facility to do that with the red lines. We have fixed pressure experiments going on. Our interest, going back to the original project scope, is to look at vorticity and circulation and the characterization of these vortices that we see in the flow. And all of that feeds into this idea of how heat can be transferred within our sheared granular material. Now, beyond my project, I have dreams, but it won't fall within my time. And I should have mentioned earlier on, sorry, I'm running out of time here, that there is another device in Marseille that Boulogne and Pierre built with a different aspect ratio. And they're working on other things, jamming transition. It'd be really great to have photoelastic grains so we can look at the contact networks. PTFE or Teflon base or a porous rock base where we can really reduce the friction would be nice. And obviously much more. So I thank you for your attention this morning. And if I've left any time, I'm happy to answer any questions. Thank you. What's up, hands? Uh-oh.
I have a question for you.
Yes.
So turbulence model has been developed starting from the analogy with kinetic theory. But here you can apply directly kinetic theory. So why using turbulence model instead of kinetic theory?
That's a good question. I'm not sure I can fully answer that. Maybe we can talk later. I think really what we found here was something unexpected, and we're just looking at a simple explanation using what we had, and that's what we came up with. We can talk later.
Following back on the same question, this has been observed and actually predicted many years ago in the early 80s by Jim Jenkins and co-workers.
Okay.
And what happens is quite simple. You have no slip at the wall.
Yeah.
Therefore, the wall is always dissipative of the granular temperature. Therefore, the viscosity goes down at the wall. Therefore, the strain rate goes up, and that's and it's been seen in simulations and predicted by theory with no problem and no need to go to turbulence.
Clearly, we are not increasing on a regime.
Yeah, there's no inertia in these. That's also part of the explanation. There's no real inertia in these flows at all.
Yeah, we really.
The viscosity, yeah, but the viscosity, the eddies are not transporting momentum, but they're showing that there's a cluster of this size, so there's force chains, so that's why this length scale works, but it's completely different from turbulence, and it's completely out of a kinetic theory regime.
Yeah, so when I say we borrow from eddy viscosity, it's just really conceptually with a length scale. I mean, we're not really doing a turbulence or fluid dynamics sort of perspective. It's really just very conceptual. To have this idea of a length scale that scales with the distance to the wall.
Have you tried to look at a fit between theory and experiment for the granular temperature?
So what's that?
For the granular temperature.
No, we look at granular temperatures and things like that.
Because I think that would be interesting to look at.
One more question.
Yeah, you seem to have like swirling.
Yes. Yes.
And have you tried, or maybe it's further along the line, but have you tried to relate this convection that you see to how does it couple to the internal rotation of the grains?
No, again, we're in the process of looking at how they're related to perhaps the rotation in the system. We're looking at doing that now. The rotations have, well, the ability to get the orientation of the grains sort of was the last couple of months, so we don't have anything solid from that yet now, but we're working on it. Yeah.
Okay, can we speak?
Break, yes.
Thank Allah. And all the speakers